welcome to the concepts video on graphs of logarithmic functions. So the first thing we're going to do in order to kick off this video is try to graph this function right here. F of x is equal to log, if I can spell log base 2 of x. Okay? So this, in other words, we can say this is like y is equal to log base 2 of x, so I can rewrite it as the following. This is the same thing as saying 2 to the y power is equal to x. Okay, so just something to consider when we're making our table. Okay, and by table I mean like an xy table, input, output. Okay, so let's try 0 first of all. So what if x were equal to 0? So we have log base 2 of 0 is equal to what? Which is the same thing as saying, okay, 2 to the raised to the what power is equal to 0. And the answer would be nothing, right? Because no y. For no y, is this equation true, right? Even if y is equal to 0, we get 1. If y is equal to negative 1, we get 1/2, etc., etc. So this is going to be undefined. The y is undefined when our x is equal to 0. Okay, let's try a negative 1. Let's see if that one works. So then our equation turns into 2 to the y power is equal to negative 1, and that's definitely not true, right? Because any power of 2 can't just turn negative automatically, right? So this is also going to be undefined. Well, we're not doing so well, are we? So let's try a positive 1. We'll go to the positive side here. So now we have 2 to the y is equal to positive 1. And that only happens when our y is equal to 0, so we found a match on that one. So now we have y equals 0. Okay, let's try maybe a 2. Okay, so 2 to the y is equal to 2, so then y is equal to 1. Alrighty, let's try another one. Let's say our x is equal to, I don't know, maybe a 4. Okay, so if x is equal to 4, then we have 2 to the y is equal to 4, so then y is equal to 2. So that's a good one. And let's do one more. Let's say 1/2 is an x, okay? So I'm just going to extend this line over here, right? So x is 1/2. So then what happens? So 2 to the y is equal to 1/2. That means our y has to equal a negative 1. Okay? So y equals negative 1 there. So now what we're going to do is just graph some of these points. Okay? So let me do that in the space right here. So we have something like this. So here's x and here's y. And we have something like 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay? So let's graph our points. So 0 and negative 1. They're undefined, so let's not do anything on the left right now. Let's just graph the points that we know. So we have 1, 0, that's a point. We have 2, 1, that's right there. We have 4, 2, so 1, 2, 3, 4, and up 2, right there. We also have 1/2, negative 1, so something like that, okay? So if we start to draw our curve, we notice something like this, okay? And it actually continues down on the left side, but as x gets closer to 0, our function drops down to negative infinity, okay? And on the left side, this graph doesn't even exist, okay? It's undefined all on the left side when x is negative, because x can't be, so x, basically, when we see a notation like this in a logarithm, whatever's inside, so the inside, this is a really important rule, inside, whatever's inside your logarithm must be greater than 0, strictly greater than. It can't be equal to, right? Because we noticed here that that doesn't work. There is no such y that this equation is fulfilled. Therefore, the inside of any logarithm must be greater than 0. Okay? Alrighty, so that is what our graph looks like. And let me write some observations of this graph on the next slide. So, I'll just say some observations here. And I'll just draw a quick sketch of what it looked like. So something like this, it crossed through the point 1, 0, and then it crossed through 2, 1, okay? And then it went down like this toward negative infinity as we went along. Okay, so this was our log base 2 of x. Alrighty, so some observations are that as our input, as our x increases, then our function increases. So as x goes this way, we can see our function going up, right? So as x increases, this is the kind of like formal notation, so as x increases, then our function value is increasing as well. That's also increasing, okay? We also see that as x increases, then our function, or our output, so our function is increasing more and more slowly, right? So we see when we started off near 0, we were increasing super fast because we weren't even moving that much in x, but our function values were skyrocketing, right? But now, as we get over here, as we move a little bit in x, we only move a tiny bit in the y direction, right? So that means our function is increasing still, but way more slowly, okay, as we go along. What else do we notice here? Let's say, okay, how about let's study the domain and range, because that's a good way to get to know functions, right, and graphs and things. So the domain of our function here was, well, we said x has to be greater than 0. It can't be equal to, it just has to be greater than 0, strictly. So it has to be a positive number of some sort. So one way we could denote that is 0 with a rounded bracket. That means you don't include the endpoint. And then up to infinity, or we could also say x is greater than 0. Either way, that can tell us the domain. Okay, what about the range of our graph? So range means the possible values of our function, right? So we see that, well, definitely here, we're going down to negative infinity. But on the right side here, it looks like we might be approaching a horizontal asymptote, possibly. But the answer is no. This actually goes to, so if we were to look at it from like farther off, we would see it going something like this, kind of, sort of. The point is that our function keeps growing to infinity as well. So our range is going to be negative infinity all the way up to positive infinity. Okay? And we do see, we can note something kind of special about this, because the domain of this guy is actually the range of 2 to the x. Okay, so remember logarithms and exponentials are inverse functions. Okay, so the inverse of log base 2 of x is 2 raised to the x power. Okay, and you know how with inverse functions, in order to get the domain and range, they're kind of just flipped, right? So this guy is correspondingly the domain of 2 to the x. Okay, because you can plug in anything you want for x, right? But the thing that you get out, the range part, that's only going to be positive, right? And not equal to 0, but greater than 0 in some way. All right, so now let's review some graphical features. Graphical features. So this is more of the nitty-gritty technical stuff. Okay, so graphical features of our graph. Let me draw that one again. So we had 1, 0, and then 2, 1. Okay, so something like that, and then it looks like that, and as it goes along, right? So we see, obviously, there's going to be a vertical asymptote at x is equal to 0. Let me label those axes here. Okay, so we have that. We also have, as x goes to infinity, our function goes to infinity as well. Okay, let's see what else we have. A horizontal intercept at 1, 0. All right, which is going to be standard for all logarithmic, well, not all of them, but all standard non-shifted logarithmic functions. This 1, 0 is going to be true, okay, for ones that aren't shifted. Alrighty, and then again, I'll just review that our domain of this guy, of this function here, is x is greater than 0, also denoted by this notation here, interval notation. And then finally, our range was just all real numbers. So like negative infinity to positive infinity. Okay? So oftentimes our domain, like I said, domain on the previous one was x is, well, I don't even have to write the parenthesis there, but x is greater than 0, right? Also known as 0 up to infinity. But wait, there's more. But the domain is oftentimes, so domain is oftentimes different than this, okay? Even though it might seem like, okay, yeah, if we're dealing with logs, then automatically your x has to be greater than 0. But that's not the case, because sometimes we have a more complicated logarithmic function. Let's do an example of that on the next slide. Alrighty, so here we see we're supposed to find the domain of this function here. And inside the log, we see something more than just an x, right? So I'm just going to call this inside stuff, or just inside, okay? And the thing with logs is that everything on the inside must be greater than 0 at all times, okay? Otherwise, your function is not defined when when the inside is equal to 0 or is negative, okay? So whatever is inside, we must set greater than, strictly greater than 0, okay? And then we just solve for x from here. Okay, so we're just going to move that 2x to the right side by adding it over, and then we just divide by 2 on both sides, so we get x is less than 5 over 2. So we could also write this x less than 5 over 2. So we see that this is different, this is definitely different than x is greater than 0, right? And the reason being is that we had some kind of transformations going on inside of our logarithm. Okay, so this isn't the standard log, but it's been shifted in a few ways, and so we get a different domain correspondingly. So that leads us into our next topic, which is transformations of the log function. Transformations of the logarithmic function. Okay, aren't those fun? Because it's like we learn the parent graphs, or also known as the basic toolkit functions, and then we have to transform them in different ways, right? So we've already studied quite a bit of different transformations, like horizontal and vertical shifting, and horizontal and vertical stretching and compressing, right? And then we saw for exponential functions, such as like b to the x power, that had kind of a little bit different formulas for the different transformations, right? And we're going to see kind of the same thing for log functions as well. So the first thing that we want to address is simply stating that typically all graphs of log functions, so I'll just write usually, all log functions are expressed in terms of something pretty simple, of the common log, which is log base 10, so log base 10 of something, or the natural log, which is ln of something, which is like log base e, okay? And the reason for that comes from the sum formula, the sum and difference formulas of, or the sum and difference properties of logs, that is, in saying that any kind of log with a different base, let's say, so here's an example, so let's say we have log base 2 of something, let's say log base 2 of x, right? So this is, we can rearrange this using the change of base formula, or the change of base property, right, and say that this is the same thing as saying, well, log of x over log of 2, and this is using the common base, right, common base of 10 for each of these, so then we just have 1 over log base 10 of 2 times log of x, and this thing here is just a constant. So that's just kind of influencing the vertical or horizontal stretching, right? Or stretching or compressing, right? So in this case, we could just convert this guy, which had a different base, like a non-common or non-natural base, and then just convert it into some equation that is easily expressible in terms of the common log, right? Okay, so that's one note to make. And the other one that we're going to start off with is the vertical shifting. So in this case, let's say we have some f of x is equal to log of some constant times x, okay? So this, we can expand this out using the sum property of logs, right? So log of c plus log of x, and this thing here is just a constant. Well, so we don't really cross it out, but this is constant, so let's say it equals like 2 or something, some kind of constant, right? So this tells us this is a vertical shift. Vertical shifting going on, okay? So on the right side, that's what it denotes, is a vertical shift, but on the left side here, that's a little bit weird, right? Because we have a constant being multiplied directly times our x, so that should affect something horizontally. So on the left side, this is phrased as a horizontal compression or stretching. Some kind of horizontal scaling. So we actually see that due to the sum property of logs, this doing a horizontal compression or stretching is the same thing as shifting your log graph vertically. Okay? So that's important because then that tells us we can kind of, so to speak, kill two birds with one stone kind of thing, where if we want to shift something vertically, that we take care of the horizontal scaling as well.